because it started. We are recording now for everyone to know. Today we have a Sefa Karaca from Turkey. He's working for Aselsan, and it's a company in Turkey and also connected, affiliated with electrical and electronics engineering at Bilkent University, also in Turkey. He's electrical engineer by trade, obviously. And exciting thing for today is that Aselsan and specifically Sefa is as involved as senior design engineer in constructing an interesting MPI system that would integrate MPI and low field MRI, and that makes it for nexMPI and this community very interesting indeed. So Sefa, without further ado, the floor is yours. Thank you.
Thank you. Thank you so much for a kind introduction, Leila, and thank you for having me. It's a great pleasure. So hello again, everyone. I'm Sefa Karaca. Today, as Leila mentioned, I would like to talk about our in-house MPI scanner at Aselsan, and I would like to discuss how we evolve it into the hybrid MPI MRI scanner. So in this work, actually, we collaborate with Professor Sartash in Bilkent University. And let me start my presentation. So this is the outline of my speech, and I would like to start with our motivation. Why do we need such a hybrid system first? And then I would like to slightly introduce you the magnetic particle imaging and magnetic resonance imaging. What are they, and what are the fundamental magnetic fields we require for performing these modalities? And then I would like to continue with our in-house MPI scanner. So actually, it's initially designed for just on MPI, and then we just transform it into the hybrid MPI and low-field MRI scanner. And I would like to discuss about how this transformation works. And then I would like to give you our results and our difficulties for the simulations and the experimental studies. So let me start with our motivation. So we can divide the imaging modalities into two parts. Actually, the first part is the anatomy-based imaging modalities. And in here, actually, you can see we use different tissue properties in order to image the human tissue, human body itself. So our main contrast comes from the human body. On the other hand, we have tracer-based imaging modalities in which we introduce the contrast agents externally into the human body, and we try to image them. So magnetic particle imaging is also tracer-based imaging modality, and the main advantage is since only signal comes from the tracers itself, there is no signal coming from the human body. It provides high contrast and high sensitivity. But we do have a disadvantage. We don't have any anatomical information, which is required for many different applications. So as a solution, actually, hybrid medical imaging is produced. And in here, actually, at the final fused image, we have the advantage of both high contrast and high sensitivity coming from the tracer-based imaging modality. And we have the anatomical information coming from the anatomy-based imaging modality. So MPI has already been combined with computed tomography and magnetic resonance imaging, and these are the two hybrid MPI and MRI systems in the literature. And this is our MPI scanner, so it's in the field-free line topology. As I said before, it is initially an MPI scanner, and we would like to perform also low-field MRI by using the same scanner, and we would like to have at the end open-sided hybrid MPI and low-field MRI scanner. So before going detailed into this system, I would like to slightly mention about the magnetic particle imaging and magnetic resonance imaging. So for the magnetic particle imaging, as I said before, it's a tracer-based imaging modality. And as tracers, we use magnetic nanoparticles. So the magnetic core is basically super paramagnetic iron oxide nanoparticles, and they exhibit this nonlinear magnetization behavior, as you can see in this figure. So we use this nonlinearity in the magnetization behavior, and there is no human tissue exhibit such a magnetic behavior. So our signal only come from the traces, only come from the magnetic nanoparticles. And luckily, we don't use any ionizing radiation. And with the organic coating, actually, these magnetic nanoparticles become biocompatible. So in order to perform magnetic particle imaging, we need to generate selection field. So this field is actually, it contains field-free region. And if our magnetic nanoparticles are outside this field-free region, and if we apply a time-varying external excitation field, which is called as dry field, since we are on the saturated range, we don't get any response in our received signal. But if the magnetic nanoparticles are inside the field-free region, now we are in the dynamic range, so they can correspond to externally applied dry field, and we can observe some harmonics at the received signal. And by this way, actually, we can detect the magnetic nanoparticles inside the field-free region. And with the help of both dry field and the focus field, we can scan the whole field of view with this field-free region, and we can reconstruct our magnetic particle image results. So this selection field could be in the form of both field-free point or field-free line topology. And in our scanner, actually, we utilize the field-free line topology because of the higher sensitivity and because it is well suited for larger imaging volume. So in the case of magnetic resonance imaging, however, we try to image basically the hydrogen atoms by using the different relaxation times. And in order to perform MRI, we need to generate first main static field, or also called as B0 field. So we use this field in order to generate the net magnetization in the human body. So it's a static, it's homogeneous field in the Z direction, and the homogeneity of the B0 field is quite important for MRI. So as you can see in this equation also, the Larmor frequency is directly proportional with the B0 field. And from the rest of the presentation, actually, I always said that we are performing low field MRI. So the low field MRI means that this B0 field strength is up to 0.5 Tesla. And I've already shown you two different hybrid MPI MRI scanners, and they're also in the low field MRI regime. So the second field, actually, we need to generate radio frequency field, or called as B1 field. And the purpose of this field is to tilt the net magnetization in the human body. It's a time-varying homogeneous field in the XY plane, and the frequency of this field should match with the Larmor frequency. So if you are on the low field regime, in other words, if your B0 field is up to 0.5 Tesla, your frequency becomes in the range of megahertz. So we should also create gradient fields in order to have the spatial information. And these gradient fields should be in the X direction, Y direction, and the Z direction, three direction, actually, and they are called frequency encoding, phase encoding, and the slice selection gradients. So in order to perform MRI, we need to generate these three fields. So since our scanner and also the existing hybrid systems are performing low field MRI, I would like to spend more time on the low field MRI. As I said before, it means the lower B0 field strength, and actually it is the case for the early MRI scanners. But with the advancement in the MRI hardware, actually, we go toward the higher and higher B0 field strength, because going higher B0 field strengths mean that we do have a higher image quality, or we can maintain the same image quality by reducing the scan time. So this is because the signal to noise ratio, our SNR, actually is increasing with the increasing of the B0 field. Its dependence is different in the high field or the low field regime, but overall we can say that it's proportional with the B0 field strength. But the problem with going higher B0 field strength is it's also increased our installation and operational costs. So there's one number in my mind. So we do have we need $1 million per Tesla. So in the conventional MRI scanners, generally 1.5 Tesla scanners, their cost is $1.5 million. So it restricts the availability of the MRI scanners. And the other problem is they require the shielded room, so the systems become immobile. So in order to reduce this disadvantage, actually, recently low-field MRI attached a considerable interest, and the main purpose is to make MRI more accessible, to make it even portable, with providing the acceptable image quality for diagnosis. So with this, actually, I would like to continue with our scanner, our MPI scanner in Aselsan, and this is the photo of our scanner. So as you can see, actually, this is an open-sided MPI scanner, which allows interventional applications, and we utilize field-free line topology. So we can generate and we can electronically rotate and translate this field-free line into our field of view, and the gradient amplitude is in between 0.25 to zero point 0.5 Tesla per meter. So when we look at our coil configuration, actually, and on the peripheral side, we have biplanar gradient coils called as CY coils. So by using this coil group, we can generate the field-free line in the Y direction. So actually, we generate the gradient in the X direction, but we generate field-free line in the Y direction. That's why we call them CY coils. So we do have another coil group. This is exactly the same coil configuration with the CY coils, but only the 90-degree rotated, not 90-degree rotated and the smaller version. By using this coil group, we can generate the field-free line in the X direction, or we can generate the gradient field in the Y direction. By using these two coil groups simultaneously with the corresponding current values, we can generate our field-free line on an arbitrary angle. And with the help of focus and the dry field, we can translate our field-free line electronically in our field of view. So this is our MPI results actually. This is our 2D phantom, and our field of view is actually 4 to 8 centimeter. And it's also possible to translate our field-free line in the third direction, and which makes our system capable of performing 3D imaging. And you can see our 3 examples in here. And currently, actually, we are performing some animal experiments on bulb sea mice, and we are planning to perform biodistribution experiments, tumor imaging, hyperthermia experiments, and we are also planning to develop our own functional magnetic nanoparticles. So this is the MPI sides of our scanner, and now let me continue with how we transform our system to the hybrid MPI and no-field MRI scanner. So again, this is our system, and this is the coil configuration. You can see 4 different coil groups in here, actually. These 4 different coil groups is used interchangeably between MPI and MRI mode. So we are using them as a dual mode fashion. And for the MPI case, actually, as I mentioned before, we generate the selection field by using 2 different biplanar gradient coils called as CY coils and the CX coils. You can see they are the blue ones. And since we generate the gradients in the X and Y direction, actually, we can use them in the magnetic resonance imaging in order to generate the frequency and the phase encoding, which provides the spatial encoding for the MRI. And we do have another coil groups called as CZ1 coils. Actually, in the case of MPI, we use this coil group in the Helmholtz configuration in order to generate homogeneous focus field of MPI. For MRI, we can use them again in the Helmholtz configuration in order to generate again homogeneous fields, and we can use them as a main static field or B0 field of MRI. So as a last coil group, actually, we have CZ2 coils, and we use them in the MPI. We use them in the Helmholtz configuration again in order to generate excitation, in order to generate the dry field. This is an homogeneous field. But in the case of MRI, we can use them in the Maxwell configuration in order to generate a gradient field on the Z direction, which can be utilized as spatial encoding gradient for MRI. So I would like to talk a bit more about the CZ1 coils actually. As I said before, we use them in the Helmholtz configuration for both MPI and MRI in order to generate the focus field of MPI while generating B0 field of MRI. So this is our field map. Actually, we just experimentally measured this field map, and these are the coil efficiency and the field inhomogeneity of our coil. And in the case of MPI, actually, we are trying to generate focus field. And this means that if we have higher coil efficiency, we can scan larger field of view, which is our main design criteria, because this coil group is initially designed only for MPI, and we have a design which maximizes the efficiency. But this is a bit problematic in the case of MRI, because MRI, so in the B0 field actually, having the higher efficiency is still great, but we also require higher homogeneity. And in our case, actually, our field homogeneity is 2000 ppm, which is quite a lot for MRI. Actually, in the case of conventional MRI scanners, our field field homogeneity is on the range of a few ppms. But the good things about low field MRI, actually, low field MRI is a bit less sensitive for this field in homogeneity, but still we do have lots of trouble because of this field in homogeneity. And I'm going to show the result in the simulation and the experimental studies. We do have lots of artifact because of this field in homogeneity. So there is a certain trade-off between MPI and the MRI design criteria. Even in the both of them, we just generate the homogeneous magnetic field. So same story actually is valid for the gradient case actually. Again, we just generate the gradient fields in the two direction. And these are again our experimental values. But in the case of MPI actually, we we require more efficient coils in order to have higher gradient field strength. So high gradient field strength means high resolution in the case of MPI. So our coils again designed for higher efficiency because initially they're just designed for MPI. But the problem is, again, there is a trade-off between the efficiency of the coil and the sleeve rate of the coil. Because if you like to have a more efficient coil, you just increase the inductance of your coils, and this means you just decreasing your sleeve rate. So as I said, by sleeve rate, actually, it's a measure how fast you can on and off your gradient fields. So for the MRI, actually, we require higher sleeve rate, and if you have lower sleeve rate, actually, it restricts your pulse sequences capability. So you cannot apply different pulse sequences because of the lower sleeve rate, and this is the case for our system. So with this, actually, I would like to continue with the simulation studies. So we just first try to model our system in our simulators, and we just try to observe whether our system is capable of performing low field MRI or not. And to do so, we generate our in-house magnetic resonance imaging simulator. So what we do is basically we just try to solve the block equations in each image pixels in order to see the effects of T1, T2 relaxations and rotations to the RF pulses, gradients, and off resonance effects. And because we have high field inhomogeneity, we perform spinnacle pulse sequences, and we model our noise as zero mu mite Gaussian noise, and we just scale our SNR with the B0, and the readout bandwidth is given in here. And for more details for our simulator, you can go and check our IWMPI paper. And also, we have already developed a magnetic particle imaging simulator. You can go and check our AMBC paper for the details of this MPI simulator. So this is the phantom we used in our simulation studies, and the base material of the phantom is modeled to have gray matter, to mimic the gray matter, and we assume that the vacancies of this phantom is filled with magnetic nanoparticles. So these are our first results for the low field MRI simulations. And on the left side, actually, we have lower B0 field strength, and for the right side, we have higher B0 field strength. And as you can see, actually, for the lower B0 field case, we have noisy reconstructions, which is expected because as you lower your B0 field, you lower your signal to noise ratio. But going for higher B0 field, yes, you can increase your SNR, but you become more sensitive to that field in homogeneity. And the artifacts, actually, you start to observe signal dephasing and the geometric distortion artifacts. So in the literature, actually, there are different scanners. There are different low field MRI scanners which utilize the B0 field of 50 millitesla. And our aim is also going for that. So we try to adjust our pulse sequence parameters in order to have the same image quality even in the case of higher B0 field. So in order to do that, actually, we just adjust our readout bandwidth and the RF pulse bandwidth of our pulse sequences. So as you can see in here, as we increasing the B0 field, if we increase also our readout bandwidth, we can avoid the geometric distortion artifact. If we increase the RF pulse bandwidth, we can avoid the signal dephasing artifact, and by doing so, we can maintain the same image quality by even in the case of 50 millitesla. So this is the results for the multimodality imaging. This is the simulation results for our multimodality imaging uh, case. And on the upper part, you see the ideal system. And for our current system, actually, although we have still having some distortions, we still have some geometric distortion, it's fair to say that actually our scanner is eligible of performing low field MRI. And with this result, actually, we just continue with our experimental studies. So at the beginning, actually, I have shown you four different coil groups, and by using those coil groups, we can generate the B0 field of MRI, we can generate the gradient fields, but we cannot generate the B1 field, we cannot generate the radio frequency field, and we just add those parts by using the dry control unit and the RF2000 amplifier of pure devices. And we add this single solenoid coil as for both transmission and receptions of the LF-MRI signal. So again, we are trying to perform MRI with 50 millitesla, this corresponding to the Larmor frequency of 2.30 megahertz. So actually, this is the reason why we don't have any coils in the case of MPI, which can be used in the MRI case, because in MPI, actually, we don't have a coil which is suitable for this frequency range. So we just add them externally to our system. But this is the only coil group. So we just add a single solenoid coil in order to perform low field MRI with our MPI scanner. So this is the full signal flow chart of our system. Actually, we can see we add this transmit receive chain externally, and other than that, actually, we use our current system. And this is the photo of our scanner. So for the experimental imaging, experimental studies, actually, we perform projection imaging. And again, because of the higher field inhomogeneity, we perform spin echo pulse sequences. And you can see our imaging parameters in here. So our scan time is around 18 minutes. This is because we perform low field MRI and we try to go with higher number of averages. And this actually increase our scanning time. And we continue with our experiments by designing this MRI phantom. This is basically the mixture of oil, gelatin, and the water. And we are just trying to capture the shapes of this three phantom. And these are our low field MRI results for our experimental studies. So as you can see, we can capture the shape of each phantom quite clearly, but still we do have an geometric distortion artifact, especially in the peripheral region of our field of view. So this is because of the field inhomogeneity value. And in the case of simulation studies, actually, we have shown that we can just minimize this distortion by going higher and higher readout bandwidth. And we would like to validate our results in the case of also experiments. And we use this phantom, actually. This is, again, the same T-shape phantom consists of just oil, water, and the gelatin. And if we try to perform low field MRI by using readout bandwidth of 65 kilohertz, you can see that we can capture the shape. We have the still we have the geometrical distortion artifact, but they are quite minimal. So if we perform again no field MRI, but we just only changed our readout bandwidth to the 30 kilohertz, as you can see, the artifacts, because of the geometric inhomogeneity, the geometric distortion artifacts become much more severe. So in the previous slide and also for the upcoming slide, we use the readout bandwidth of 65 kilohertz, but we cannot go higher than the 65 kilohertz because of our hardware limitations. So in order to going a higher and higher readout bandwidth, you require the gradient field, you require the high gradient field strength, and also you require higher slew rate for your gradient coils. And our coils actually allows us, at maximum, allows us the 65 kilohertz, and we are just live with it. And the second experimental studies actually are called contrast experiments. So yeah, we can capture the shape of the phantom, but in order to perform LF-MRI, we also provide different contrast for different tissue materials. So in order to show that, we create this phantom. Again, this is the tissue part, and at the center, we just insert the PCR tube. And in the first case, actually, we just filled the PCR tube with oil. And in this is the results for T1 weighted imaging. And in here, actually, the oil T1 value of the oil is smaller. And as you can see, we can just see the oil part quite brighter. So this actually validates that we can provide different contrast for different tissue materials. In the second case, actually, we add the perimag, which is a magnetic nanoparticle in this PCR tube. And in this case, actually, you can see that we just kill the MRI signal in here at the center. So actually, that is what magnetic nanoparticles what it do in the MRI scanners. So they just create local inhomogeneity and kills the MRI signal. So that is why we don't prefer MRI to image those magnetic nanoparticles. They are creating negative contrast. But with MPI, we can image them with high positive contrast and high sensitivity. And for the third case, actually, we just filled them with only perimag, and again, the same result. Again, it just creates the negative contrast at the center. So with this result, actually, we validate that our system is capable of capturing the shape of the phantom and providing the different contrast for different tissue materials. So with these, actually, we can say that our system is also eligible for low field MRI, performing low field MRI. But we would like to continue with also MPI experiments to have multimodally imaging. So this is the full signal flow chart for our MPI case. And again, we use the same scanner for MPI. And for the MPI, for this study, actually, we use the selection field gradient of 0.25 Tesla per meter, and we perform system matrix reconstruction. And with this configuration, actually, we continue our multimodal imaging experiments. So this is the same phantom in the case of contrast experiments. As you can see, we have the tissue parts and the magnetic nanoparticles part. So the tissue is so if we perform low field MRI, actually, we can image the tissue part. So the magnetic nanoparticles create negative contrast. We cannot see them. But if we use the MPI mode of our scanner, in here, we can just image the magnetic nanoparticle distribution with high contrast, high positive contrast, and high sensitivity. So at the end, in the overlaid image, we do have the advantage of both anatomical information and the magnetic nanoparticle distribution with high contrast and high sensitivity. And this is the same story, but a bit complex phantom. In this case, we have two PCR tubes. And if we perform low field MRI, actually, you can see our results for the low field MRI case. We just reconstruct the tissue part of our phantom. And if we perform MPI, we can reconstruct the magnetic nanoparticle distribution of our phantom. And at the end, in the overlaid image, we have the advantage of, again, both anatomical part and magnetic particle distribution. So with this, actually, we also validate the hybrid performance of our system. And to conclude my presentation, actually, we proposed a novel scanner, novel hybrid MPI and no field MRI scanner. And the main advantage of our system is we can use our coils interchangeably between each modality, interchangeably between MPI and LF-MRI modes. The only one single coil addition required to perform low field MRI, but other than that, we use them in a dual mode fashion. So we can image the magnetic nanoparticle distribution with MPI modes, and we can have the anatomical information with the LF-MRI modes. So with this, I would like to end my presentation. Thank you so much for your interest. And if you have any question, I'll do my best to answer those.
I'm trying to unmute myself. I think that works now. Sefa, thank you. Thank you so much for the presentation. Interesting. We usually have a lot of questions, so I'll let the audience start with the questions. Do we have already any questions from the audience? Can't see any hands. I could kick off with starting with the question and then see further, because you did say at certain point you intend to do preclinical trials, I suppose, considering your relatively low bore size of, was it 2.5 centimeter in diameter? That would be mice usually, right? Is that correct?
Yes, biopsy mice. We are trying to perform, but we don't planning to perform low field MRI. So we are just trying to go with the MPI part of our system because let me show you these results actually. For the case of MPI, actually, our field of view is 4 centimeter to the 8 centimeter, and our aperture is 3 centimeter. So it's well suited for the imaging the biopsy mice. But for the case of low field MRI, actually, our bore height is 25 millimeter, and we should increase our bore height for that preclinical.
Do you have, and thank you. Do you have any idea what is the timeline? Because from my perspective, I would be interested in having a hybrid system providing both MPI and MRI images. Because you did mention we intend to go into, for example, biodistribution studies. That would mean that you need to segment specific organs in order to study biodistribution for either medication or only nanoparticles, whatever you want to do biodistribution for. But that will imply you have both images. So my question is, what is your timeline before you would be able in let's say the crudest, the most draft prototype you could make to perform hybrid imaging on mice, for example.
Yes. So actually, this is our timeline for the MPI case. Actually, we are planning to start with biodistribution experiments, and then we are trying to perform tumor imaging. And so, as I said before, actually, we are trying to perform these animal experiments only for the MPI modes. So, at the meantime, actually, we are trying to develop our all different transmit and receive coil for LF-MRI in order to increase our bore size. So, which makes also low field MRI modes suitable for the biopsy imaging. But we are trying to do this on in a parallel version actually, and at the end we would like to have also low field MRI for biopsy mice, but this is the timeline for only the MPI
But
modes. But at the end of the functional magnetic nanoparticles, actually we are planning to perform these approximately in the 6 to 7 months. Actually, at the end of that we also insert our new coil, our new solenoid coil with the increased bore size to perform low field MRI also.
just for my clarity, next year, IWMPI, you will be able to present hybrid mice images. Is that correct?
Yeah, I hope so.
Okay, good to know. Good to know.
Yes.
That's the type of. But in anyone else, in the meantime, any other questions?
Can I ask a question, Leila?
Yes, please, George. Go ahead.
I would like to go to slide 49, where you showed the hybrid images.
Yes.
Yeah, coming from a pet background, I see you have. Let's go to 49. Yeah,
This right? Yeah.
yeah, yeah. Both 48 and 49.
Yeah.
You do have you have a distorted background, right? I mean, uh, isn't it distorted, the background, the MPI, the MRI image on the background, or
Yes,
not?
for
Yeah. Is it something you think will limit the use of a system like that when it comes to animal imaging? Is it
yeah,
something can be improved?
yes. So the main distortion is because of our field inhomogeneity. So we have huge inhomogeneity, 2000 ppm, and in order to get rid of those distortion, actually, we need to improve the inhomogeneity, and we are planning to add some extra shimming coil in order to improve that inhomogeneity. And
Okay.
by doing so, we can just reduce this distortion, or we can just minimize them.
Okay, so it's something that it could be improved in the future. We were
Yes,
working
yes,
towards
yes,
that.
yes,
Okay,
yes.
great.
And,
Especially
and
for the preclinical imaging, yeah,
And I think we
we need to
have to
improve.
assess to what extent is that actually distorting whatever, because basically what we want when we start with biodistribution, right? All you have to know to do is segment your liver. And the
Yeah.
question is, how far is what we see now in MRI artifacts? How far is that this actually influencing organ segmentation? And now I'm afraid the proof is in the pudding in this case, because there is no other way than trying and see
Yeah.
what happens. There is a one written question in the chat box from Mustafa Utkur. Thanks, great presentation. My question is about the B0 MRI field. Since it's resistive foil, how are you making sure the B0 field is not fluctuating? Do you have a temporal stabilization system? And another question is, what is your B0 in the homogeneity?
Yes, so it's a great question. So again, yes, we use a resistive coil to generate our B0 field, and actually so the question is, how are you making sure the B0 field is not fluctuating? So we are not sure. So that's why we have huge number of averages, and we also try to apply some temporal stabilization systems, but it's a bit complicated, and we try to just use lower TR value in order to minimize the effects of the this fluctuating because of the temperature, actually, and we are just going for the higher number of averages. But we see we most probably, actually, in our case, we do have a B0 field fluctuation, and we can see the results because of the phase shift in our spinaco signal. But we are just trying to live with it by using high number of averages. And our B0 field inhomogeneity is around 2000 ppm.
Hopefully, Mustafa, that answers your question. I don't see anything. In the meantime, are there any additional questions for Sefa from the audience? Seems like not. I suppose you're going to MPI, and I'll see you there and talk
Yeah.
to you. So that would be great. I love development. It's wonderful. I think that's exactly what we need. We just need a bore size to be like 0.5 meter instead of 5 centimeter.
Yes.
Do you have any vision from your side on when are we going to able to when can we expect such a system with significant bore size to come from Aslan? Or are you not going for that at all? That might be also.
Yeah, so actually at the beginning we are planning to increase our bore size. We are planning to transform our preclinical system to the human size scanner case. But we are initially trying to do this in the MPI mode only, because MRI is just getting too complex in the case of human size scanner. We need to add lots of different coil groups. We need to increase our homogeneity of our B0 field. We need to add shim coil. We need to increase the bore size for the also LF-MRI case. And at the beginning, actually, we are just trying to get rid of that complexity, and we just focus on the MPI part for the human size case. And so at the end of our animal experiments, actually, we are trying to build our human size scanner. So we do have an initial design, but we need to work on that a lot, and we need to produce that initial design. But hopefully I don't know, most probably in the next year, at the end of the next year, actually, we are fine with the design, but the producing part, I don't know, maybe it takes a couple of years more.
Okay. Okay. Well, so it's nothing we could expect next year. So hopefully with good hope in 5 years or something. Maybe I missed it. I think you're working on half a Tesla scanner on MRI side. Is that correct?
No, we have 50
50
millitesla.
50
Yeah,
millitesla,
50
right? Yes,
millitesla.
yes.
Yeah,
Great.
I've just said that up to 0.5 Tesla, actually, we call them low field MRI, but we are performing
Definition
50
changes,
millitesla.
I suppose.
Yes, sure.
Yeah, it's a shift in definition as well. Okay, I see no other question from the audience so far. Okay, great. In that case, Sefa, thank you very much for your presentation. Always interesting to see new developments. Take care. Have a nice evening, everyone, and hope to talk to you soon. Take care.
Thank you
Bye-bye.
so much. Good evening.
George, we can stop.